I'm going to do that. Okay. Excuse me. Okay. I'm gonna put you on the ground. I'm sorry, honey. Here. Whoop. There you go. Okay. Bless you. Alrighty. Welcome to class, everybody. As far as I know, it is Wednesday at 11:30. Looks like the viewership is a little bit lower than normal right now. Maybe that's just a bug. But we'll get started anyway. All right, looks like more people are showing up here. So once again, happy Wednesday and welcome to the stream. So let's just talk about a few things. First off, Last night, the assignment was due. I know some of you guys ended up asking me some questions, and so hopefully you were able to get that assignment working. Assignment 8 is posted. Today I will cover that one. This one is a tiny assignment. This one's very small, just in the amount of code that you have to write. It's a tiny assignment, and it is just a little bit of recursion. Everyone in the department is doing this assignment, so I didn't make this one, but I do know how it works, and I can be helpful to you in that sense. So if you have the questions, please ask them. I will pretty much be covering one of the functions that we do in that assignment today in class. It won't be verbatim, but it will be almost exactly the same. So at least you'll get some help with one of the functions. And then I also did add comments. So I added plenty of comments, kind of hints like I've done in some of the past assignments. So that should be helpful to you as well. And like I said, I'll go over this at the end of class. So if there's any questions that you guys have for that assignment, you can ask them. Once again, this upcoming assignment is rather small. And you definitely, though I never recommend waiting until the last minute to do your assignment. Compared to, say, maybe assignment 7, assignment 8 might be more doable within a shorter amount of time. So today we're just going to do some more recursion examples. Plenty of them. I've got a bunch of examples already typed out, and we've got a bunch of different things. Okay, so we kind of got the math. That was with the power function, right? We might get to log today, though it's not on the schedule. We've also got some printing, how to print things recursively. For example, in the assignment, you will be asked to print a matrix recursively. And so I will actually be doing that for you today. So we'll have an example of that. We'll also have an example where we print a triangle recursively. I know that you guys, well, at least when I took CS 135, we had to print a triangle. Have you guys printed triangles before? And if you haven't, I might kind of throw that example up, but that is kind of one of the for loop exercises. Yeah, so Awful says you had to print triangles before. So we'll kind of do that with recursion instead of loops. And then what else do we got? We will do the Fibonacci. CBA says you haven't printed triangles before, so I'll go over that. Right, Awful definitely not with recursion before, so I'll be doing that today. But before we do it, I'll be sure to do the for loop version of it as well. Just because CBA says that they have not printed triangles before, so it would be good to kind of cover that. And then the other two things that we'll go over is we'll do a substring function, and we will do a, let me check my notes. We'll do a substring function, and we will do we'll do the Fibonacci, right? We'll do the Fibonacci. So we've got a lot of stuff going on. Let's just kind of check these very small notes that we took, just to refresh ourselves. So if you remember from last time, a recursive function is a function where the definition of the function includes a function called to itself. And I kind of talk about this idea in which to think recursively is the idea. So there really is no, I would say, kind of set in stone method to convert. I'll say there's no no easy method to convert loops to recursion. Okay, and so the only reason I say that is that, you know, You can't always just take your program with loops in it and just like feed it into a machine and out will pop a recursive definition of that function. That's all I mean to say like that. And so when we're talking about thinking recursively, it's just kind of a mindset we have to put ourselves into in which we need to break the problem down into smaller problems. At pretty high level, there's some publications in regards to doing this, converting loops to recursion, recursion to loops, but we're not going to cover that in CS202. And as of right now, we've been thinking in iteration all the way up until this point in time. Whenever we want to get through an array or we want to do something over and over again, in general, we use loops. We haven't really touched on recursion yet. And so then I just talked about Alan Turing, in which we say that anything that uses a loop can also be solved using recursion. And I told you in these classes here in CS326, you'll probably learn about Lisp, which is a programming language that has no loops in it. So you have to be completely recursive. And so now it's a good time to start thinking about this kind of thing. Seabay asks, is it wrong to think of recursion as kind of a while loop? I wouldn't say it's necessarily wrong, no. I'd say they're very similar in a sense. I think it's okay, but I think that you'll kind of develop a better understanding of recursion as we continue on today with some examples. And in a way, and I guess I'll just mention this. We're gonna just touch on this power thing. But whenever you do, say, some for loop, and then you nest a for loop inside of it, this can kind of be seen as maybe a tree. Of course, I'm just giving an example here. A tree, and let's say if this is maybe n, for I is less than 5, something like that. I'm just doing pseudocode here, okay? This code doesn't work. But let's say this is going to iterate 5 times, and this will iterate however many times. In this case, it doesn't matter, so this is going to be like the big for loop. And then we're going to have the small for loop in there, and it's going to iterate out 5 different times. So you'll kind of get 1, 2, 3, 4, 5. And so, of course, CB, I think you're right, and there can be kind of similar. And then Awful asks, are trees not general? And are you referring to when I'm talking about like simple solutions to things? When I was talking about being general last class? Because what I would say is that with recursion, we usually simplify the problem so much that it only really deals with only a few cases. And I would say that recursion is one of the most general coding styles there is. So I would say trees are pretty general. And so what did we say about recursion? Well, recursion is memory intensive, and in general, it's slower than looping. So why do we use it? Well, some problems are hard to think about using iteration. We're going to start doing kind of linked lists here pretty soon. And so recursion is going to be very helpful for that. And as I said, recursive solutions are often elegant and simple. So Awful, you were talking about that. When I say simple, usually it means kind of general as well. So recursive solutions are quite general. They're quite generic. And they can be easy to code. And so always remember what is the basic idea of recursion, and it's to break the problem into smaller problems, to the smallest possible problem that it can be broken into, kind of like building blocks. And so what three things will a recursive function always have? A recursive function needs to always have a reduction operation, which takes us a step closer to the base case. The recursive function also needs to have a base case or more. I can say one or more base cases. And the base case returns. It stops, right? This is kind of like the while loop, the Boolean check inside of the while loop, right? It says, all right, now we're done. And so now we'll just kind of come back up the tree in this case. But if we're thinking about it in terms of loops, this will stop the loop. And of course, the thing that makes a recursive function recursive is that it calls itself. So a recursive function will always have these three things. And then I kind of got a little caught up on myself, or a little ahead of schedule last class when I was talking about the binary tree. And so I want to clear that up. So I said however many function calls are in the function are in... I'll have to fix this. Here's what we'll say. The most amount of times that a function will call itself inside one block of code is how many leaves the tree will have. So let's just read this real quick to make sure that it kind of makes sense. And then we'll talk about this, of course, in this example that I have ready to go. And so I say the most amount of times that a function will call itself inside one block of code. Or call itself from one function call. I'll edit this a little bit, but this is how many leaves that the tree will have. So let's kind of just look at some examples of that. And I'm going to correct my little mess up from last class. And so roughly here, this is the power function that I coded last class. I'm pretty sure this is almost exactly, if not exactly, the one that we did, except I've changed its name to unary power. And the unary means that this is a unary tree in that... there will be only one leaf per node. And so I'll talk about that on the whiteboard in just one moment. But notice here in the comment, I say that this recursive function, it will only make one call to itself at most. And kind of said here in one block of code. So if we look at the two cases, this function will either execute this block of code or it will either execute this block of code. And so if we look inside of this function, how many times at most will this function call itself? In this case, it doesn't call itself at all, so this could be considered 0 times. And if we look inside this block of code, how many times does this function call itself? Well, at most here, it calls itself 1 time. And so I will take down here 0 versus 1, or rather, if we took the max of either 0 or 1, it's equal to 1. Therefore, this will generate a unary tree. Now, I said last class that this is a binary tree, and so I'm just going to correct that right now, and we will make a binary power function, but I will just show you what this looks like real quick with 2 to the third on the paint diagram, and I'll just kind of correct myself here. That's kind of sad, but I can't fix it. That's not what I said. Yeah, it's okay. So here we're going to have our big problem, okay? So in this case, we're just doing a refresher here. So this will be 2, and let's say control, I think, shift equals 2 to the third. And so if we just reference this code, and I did this last time, of course, but we're just going to call itself by taking whatever the number is, which is 2, and recalling binary power with the same number, but it's going to be the exponent minus 1. In which the exponent minus 1 is the reduction operation in this case. So I'll actually just copy it, and it actually will look more like this. 2, 3, 2, 2, 2 to the 1. I'll have to make this a little smaller. And then finally down here. And so I'll actually clean this up because we can't really see it. So this one will be 2 to the 3rd. This will be 2 to the 2. This one will be 2 to the 1. And then this one will be 2 to the 0. Now, what's happening every time that we call itself is we actually are multiplying 2 by each value. So down here, we're actually going to return, this is the base case. So this kind of returns 2 times 1 here. And I'll make it maybe red. And so then what this guy does is he comes back up to this function here. And we'll just say that this is the 2 times 1 here. And then it's multiplied then by 2 again. And then we can actually just copy this little bit here. And so then it comes up to this function where it's multiplied by 2 again. And then it finally just comes back up to this function here. Actually, I've made a small mistake. I apologize. So I'll just fix it. Down here, it actually returns 1, right? I had made a mistake there. If we look here, when the exponent is equal to 0, here it is. The exponent is equal to 0, right? And so actually, it just returns 1. Just returns 1. That's it. Right. Yeah, you're correct. That was a mistake of mine. So it just returns 1 here. And then when it comes back up, it takes 1 times 2, and then it comes back up and takes 1 times 2 times 2. And then it comes back up again to this final node here. We're going to kind of squish it down a little bit. And then this will give us our final result of 1 times 2 times 2 times 2, which is equal to 8. So is that fair? And are there any questions onto why this is going to be considered a... Whoops. Actually, a unary tree. Thank you. Yes, I think it should make sense. And this is only a unary tree in which the blue circles are considered the function calls. So we'll go ahead and save this, and this will be our unary power picture. And now I will just show you the binary power picture, and I'll just code the exact same function. But it will look a little different. It'll look a little different. So I'm going to keep this same thing here. So every recursive function needs that base case, right? So let's keep the if exponent is equal to 0. But then there's actually going to be a few more things that I check. The next thing that I'll check is I'll see if the exponent is equal to 1. And if it is, I will return the binary power of the number, exponent minus 1. But in this case, I'm going to multiply num by this. Okay, so it's actually going to be the exact same thing that we did here, except it's only going to work this way for exponent is equal to 1. And then finally, I'll do an else statement. I'll do an if else else. I will return, and I'm just going to copy some things here. It looks like we're having around our noon stream outage. So I'm just going to wait a few seconds, as always, to make sure that we all get caught back up. And hit refresh if you haven't. And we will continue on here. I'll check my OBS, and it looks like we're green again. So we'll get going. Okay, so in this case, I've added this extra else statement. Now it's kind of redundant. It's kind of ridiculous that I've done this. That I would call binary power again at 1, right? Because this is exactly the same as, you know, num times binary power. But I'm just trying to make the point. And so when I want to know what kind of tree this makes, I'm going to look inside this function, and I'm going to see at most how many times this function will call itself in one call to itself. So I'll check this block, right? This is case 1, and it calls itself 0 times. And then I'll check case 2, and in this case it calls itself 1 time. And then finally I come down to this case statement, and I say in this case it calls itself 1, and it calls itself 2 times. Calls 2 times. So I'm going to ask for class participation here, and then we'll put this power thing to bed. Looking at this function, what kind of tree will this generate? Just looking at this code, what kind of tree will this recursive function generate? And Red Rose asks, would it use more memory? So the more trees, the more memory use. That's correct. It's kind of like the more function calls we make, that means the more... and I'll kind of explain that in just a moment. I like that you've asked that question, but I do want to check... Let's look at this. We did this last class. Yeah, so thank you, Awful. That is correct. That it makes a binary tree, right? Pretty obvious. And so actually last class, I had made this tree. And so this happens to be the binary tree, okay? So this tree that I made last class more corresponds to this function that I've written now. And this one corresponds more to this tree. Okay, so hopefully that makes sense. And I'll talk about Red Rose's question here. And so every time you call a function, notice that these, well, even if they weren't, notice that these variables are provided to the function, right? And so whether or not they are passed by address or not, and in general, if you're doing recursion, definitely do not pass this by address. But even if they were, this function instance has to have its own stuff. So if we kind of look in here, these blue circles are the function calls. So if these blue circles are the function calls, then this guy needs its own num and exponent. And this function call also needs its own num and exponent. And this function call also needs its own num and exponent. And this function call also needs its own num and exponent. And so the more times we call the function, the more memory that we're going to need so that each of these functions can have their own frame to look at their own variables. Because this num and exponent is different from this num and exponent, and this num and exponent is different from this one. So in this case, this one will actually use less memory than this one. It looks like this one calls itself 1, 2, 3, 4, 5 times, and I think that's correct. Well, 2 to the 1 here, right? Yeah. So I actually call itself maybe a little bit more than that. So most definitely, This one here will take more memory than this one. And that's only because it calls itself more times. So hopefully that kind of answers your question. And the reason it takes more memory is because we have to pass things to the functions. So now we'll come back to the Fibonacci sequence as we were ending with last class. So I'm going to just pull back up that thing, that Wikipedia, where I could see the definition of the function, and I'll just take a quick screenshot of it so we can look at it. And let's put it into some code. All right, so here is our Fibonacci sequence. And so we determined, yeah. Let's see, can you paste the code you're working on Discord? I'll give you this one. But I'll also upload it to Web Campus at the end. So we did talk about this last class, so I won't spend too much time on this, but we identified these as the base cases, and we identified this as the actual recursive function. And I appreciate that, Awful. I'm glad that you are following along. So all we have to do is code this up. And so the Fibonacci sequence, in case you haven't seen it before, there's like a bunch of, well, not a bunch, but there's definitely a documentary talking about how the Fibonacci sequence is like everywhere around us and stuff. But here it is. And so they say here that f of 0 is equal to 0, right? And so if I'm going to kind of give you a pretty lame handwritten thing, but this here is f of 0, right? And then this one is f of 1. I can't write with my mouse, but this is f of 2. This is f of 3. This is f of 4, f of 5, f of 6, f of 7, f of 8, f of 9, so on and so forth. So we can kind of think of it like maybe f parenthesis x, if you would prefer to think about it like that. But they're using this subscript notation instead. And what it is they're integers, right? So we're going to do int fib, and all it takes is a number. All it takes is an int number. And so what are our base cases? Well, we're going to check for if number is equal to 0, right? And if that is equal to 0, then we can return num in this case if we want to, because num is equal to 0, and f of 0, fib of 0 is 0, right? So that's base case number 1. So now we'll do base case number 2. And so we'll just check here now if the number is equal to 1. Then we'll go ahead and return. Actually, let's clean this up, right? Because if I return num either way, then it won't matter. So how about we do this instead? I think that you guys will prefer this better. Say fib of 0 is 0 and fib of 1 is 1, right? Those are the base cases. So we'll just return the number instead. So this will just be kind of our only base case, but these are the two cases, right? In the case that num is equal to 0, or in the case that the num is equal to 1. Else, we're just going to return the fib of num minus 1 plus the fib of num minus 2. So in this case, I already told you what the base case is. What is the reduction operation? for this Fibonacci function. We know that the reduction operation will take us closer to the base case, right? And so whenever we call Fibonacci, we call it with num -2. And so the reduction operation is either the -1 here, or it's the -2. Yeah, CBay, you're 100% right. It looks like maybe my stream hiccup that we had earlier has set us back a little bit. So as long as we keep that in mind, then we're good. You guys are both correct. These are the reduction operations. And I promise you, if I called it like this, your function will go on infinitely. You'll get a stack overflow. You've created an infinite loop. And so it will just call fib over and over and over and over again. And you'll have a major problem. So let's just kind of run this in Bobby. And let's see if we got the exact same sequence that's on Wikipedia. Let's see here. Just want to make sure that we got it right, because we should see 0 to start. So I may have made a... Oh, I see. I made a small mistake. Sorry, folks. I loaded the wrong file. I loaded my notes file. There we go. So let's kind of pull up this thing here. So you notice here we've got 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, so on and so forth. And so we got that right, okay? And so we just kind of coded that Wikipedia function as a recursive function here. And I'm going to get started on the next example here. And while I'm doing that, can anyone tell me what kind of tree this makes? And the next one we're going to do is a fun one. Well, we'll start with the print triangle. Right, that's 100% correct. It makes a binary tree. And the reason is, whenever you want to know what kind of tree it's making, we'll just kind of look at all the cases. It'll say, in this block of code, fib does not call itself at all. So it's 0 calls to itself. In this block of code, it calls itself 1, 2 times. And so since it's 2 times, it's going to make a binary tree. So we're going to work on this triangle thing. Some of you have printed triangles before and some of you have not, so I'm just going to do that real quick. So our height of the triangle will be 5. And I'm going to ask for some participation here. And not in this instance, but notice here I've got 2 for loops going on. I want you to think about how we might be able to do this recursively. Now, I will not ban you from using loops, okay? So your recursive functions can contain loops in them, and they still might be considered recursive. Okay, so just be thinking about how we might do this as a recursive function. So right now, all I'm showing you is how we would print a triangle, similar to maybe some of you did in CS 135 or in any other programming courses that you may have had. And so let me just make sure that this is going to work. And so I want my triangle to be 5 high, so I'll just kind of print, or I'll show you what this looks like in a comment. So this kind of function will print, it looks like it will print nothing, and then it will print an x, and then it'll print xx, xxx, xxxx, and then xxxx. You see that's a triangle? It's a terminal triangle, right? This is not a very pretty triangle, but it is a triangle. And so when I is equal to 0, it will see if it can print anything as long as j is less than I. And so as I gets bigger, j will iterate more. So in this case, this is I is equal to 1. This is I is equal to 2. This is I is equal to 3. And then so on and so forth, right? This is 4 and this is 5. And the j's are the x's, right? So in this case, you have jjj, jjjj, jjjj, and then 5 j's, right? Oh, yeah. And not a three-dimensional. And Krevening might be right. It might stop at 4 instead. And that's correct. So we'll do a less than or equal to. How about that? See, someone's done triangles before, or they just understand for loops very well. And at the end of every row, we'll see out an end line. So let's just prove to ourselves that we're going to print a triangle, and then let's make this a recursive function. And we're going to kind of go halfway on this. It's not going to be 100% a recursive function, but it will be a recursive function. And all I mean by that is that we'll keep a loop inside of the function. I've definitely made some error here. Sorry, I put an end line there. I always get ahead of myself. The end line definitely shouldn't go there. But you can kind of see there's the 1 and there's the 2. But we'll fix that real quick. All right, there we go. So you can see we got our triangle here. So let's go ahead and make this a recursive function. So all I'm going to do is maybe make a void. Print triangle function. And I want it to take maybe the int height. And let me check my notes here. So does anybody have any ideas? Here's what I'll give you for now is this. So we will do a for loop here. So now, if there's two things I need. For one, I need a base case, and for two, I need a return statement somewhere. So I'll kind of put it here. This will print one row. And then we need a recursive call, and reduction operator. So Sibe mentioned earlier that he thought kind of as recursion as a while loop, and I think that's great. So what you're seeing here is I'm replacing this outer for loop with recursion. And so we've got Sibe, exactly who I was just talking about, said base case would be if the height is 0. Red Rose says if the height is 1, which I'm okay with that one as well. Either of those. Yeah, if the height is 0 or 1. And the reduction would be height minus 1. Yep, so you guys are completely, you're completely understanding here what I'm getting at. So I'm very happy about that. So let's say if height is equal to 0, then we'll just return ourselves back up. And then we'll make a recursive call with that same reduction operator. And so all we'll have to do is say print triangle. And in this case, we're going to take the height -1. And let's just say if the height is less than or equal to 0, or sorry about that, less than or equal to 0, just to kind of rule out so many things. You know, someone says print a triangle with height -10. We've kind of done some error handling here. And so this is a recursive function. Why? Because it contains a base case, a reduction operation, and a call to itself. What kind of tree does this recursive function generate? All right, so they're a little backwards. We could fix that. And it looks like we're ending up here with 2 at the very tip top. So let me see. Let's do it that way. We'll take out that less than or equal sign. And that should fix our problems here. Yep. All right, so we've got some trees, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you have it. So we've made a recursive function that prints that. And Red Rose is correct. It's a unary tree, and we are using this loop. So I'll leave this for you at home. If you want to replace this with a recursive call to itself somehow, I'll let you think about that one. And maybe we can come back on Monday and revisit that. But with the remaining 30 minutes, I would like to make sure that we cover the matrix, printing the matrix recursively. So let's go ahead and do that one. And then I also want to get to the substring problem. All right, so I don't want to scare you guys. I've already coded this, but I coded this exact class last week when we did templates. Now, I've changed this one up a little bit, okay? So last week, it looked more like this, where I had made a template matrix, and this would have been a type. But this time, we're just going to make it a matrix for characters. And this represents kind of your assignment, okay? So the assignment, you're dealing with a character matrix. And look, I showed you how you can allocate that. I also showed you how you can initialize that, right? I also showed you how you can deallocate it. So this code is all available for you on Web Campus to help you with the assignment. Now, if you recall, we did this print matrix function here. It's a little big, maybe. And so notice in here we've got 2 for loops. And so let's do it recursively. Let's go ahead and do it recursively. So the first thing I'll do is I'll make a void recursive print 1. And I'll make a void recursive print 2. We'll do it 2 different ways. And so somewhere in this function, we will have a cout matrix. Recall we're working with a matrix now. Somewhere in here, I'll have like maybe an R and a C. There are going to be some things that I will add to this function because we need some sort of reduction operation. And in general, unless we're working with a global variable, the reduction, the thing that's being reduced needs to be passed as a parameter. That might be good to add for our notes. I'll just kind of put it here. In general, unless working with global vars, the variable we perform a reduction operation on is a parameter that is passed. The variable that we perform a reduction operation on is a parameter that is passed into the function. So I will add some things to this. And I kind of want to do this R and C thing here, right? Does anyone know what the R and the C stand for? I'll let you take a guess. Last time we did it a little differently. So somewhere in these functions, we'll do a cout. And so we'll start with a simple one. Yeah, row and column, that's correct. I kind of already made these changes here. So we've got the rows and we've got the columns. So that's the R and the C. But there's a few things that we need to check for. Now, I promise you this one will not look like your traditional recursive function, but it still has all of the elements of a recursive function in there. So let's kind of think about how we can break it down. So to start, let's look at this one. Notice here we've got the two for loops. Let's just try to do the one where we replace this one here. So I'm going to ask for a little bit of help, but I will copy this one to start. So this is going to be the kind of the easier version. And this function is still considered recursive, so you're still welcome to use this one in your assignment if you'd like. So let's see here. Since we're working with a J instead of the C, this one we actually don't really need to pass a C into it, right? And instead, we will just pass, let's make this the C here instead. And let's go ahead and add our comment here that says this prints one row. And Sibe is right. We're going to be working with this O stream here, so we're going to out it in case this happens to be maybe a file. So this prints one row. So now I'll ask, what do you think the base case would be in this function? And what do you think the recursive call would be in this function? This will kind of look like the triangle one that we just did, right? Here's one row, and here's the cout. And so we might have an if check up here, and we might have a recursive call down here. Okay. And the row could definitely be considered the height. Right, so Sibe says check to see if you've completed all the rows. So how do we do that? Well, in this case, we're working with a matrix class, right? So in fact, up here, we have this rows parameter. And you'll notice that in this parameter constructor, the rows is initialized to be the height of that matrix, right? So whatever or however many rows that this matrix has, it's going to be stored in this value. So Sibe says, can we check to see if we've completed all the rows? And that's correct, we can. And so that might look something like if R is greater than or equal to rows, right? So with this in mind, with the base case in mind, what does the recursive call look like? I'll give you a hint, right? It's at least this part. But how can we call this function so that it takes us one step closer to the base case? How can we call this function so that it takes us one step closer to this base case? And I assumed that down here we would probably have maybe a matrix M1, and let's say it's a 10 by 10 matrix. And we would call M1 recursive print, and we would maybe pass C out, and we'd maybe start at row 0. Yep. Yeah, Sive, you got it, right? So we'll just pass this R plus 1. Does that kind of make sense? So we'll go ahead and test it out here real quick before we move on. But this one kind of looks like the triangle one that we just did. In fact, it almost looks exactly the same, except in this case, our for loop's a little bit different. Our for loop's just a little bit different. I'm going to add maybe a space here, so we can see that it's a matrix. But yeah, that's pretty spot on. So let's go ahead and give it a shot. And let's see how well we did. There's a good chance that we've made a mistake, and that's fine. We'll just fix it. But I'm guessing this one will work just fine. That looks like a 10 by 10 to me. I know that Awful said he wants to follow along here, so I'll give you this part. So now we're going to try this again, except we're going to try to remove this. We're going to try to remove this function here. So yeah, so Red Rose asks, Red Rose asks, would it print it backwards? If we were to print it backwards, we might start at, like, say 10. But we can't really access that variable, and then we would have to do R minus 1, and then we would have to say R is greater than or equal to 0, right? But yeah, you could totally do it that way. You're thinking along the right lines. So now we're going to do the second one. Now this one's going to have a few base cases. Maybe just 2. And so I actually have a method. I actually already have some code that we did for this, but I kind of want to see if we can do it ourselves here. So I know that we're going to have a C out somewhere, and I know that somewhere in here we're going to have a C out end line. So let's see what we can do. And I will say that if rows is greater than or equal to rows, that's probably going to be a good indication that we need to return, which means we have nothing left to print. What do you guys think about if C is greater than or equal to columns? And so that would be that, let's say we're here and we've printed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're sitting here and then C becomes +1 and now we're here. Do you think that we should return, or do you think we should do something else? Because it kind of looks like we have some more to print, right? See what we see here. Yeah, so someone says reset R, right? Or reset C. So yes, CBay, you're 100% correct. We're going to reset C. And Red Rose, we're going to change R. So let's go ahead and do our recursive print. Let's go ahead and call it. And there's two things that we're going to do. For one, CBay says we're going to reset the columns to 0. So that's 100% correct, right? We're going to reset that column to 0. Because we're kind of here at the end. So we're going to reset it back to this one. And then we're going to say R plus 1, right? Just like we did in the last one. So this one will be R plus 1. I also want to do this. Are you okay with that? So we'll actually kind of take it out of here. Yeah, exactly. Red Rose, you nailed it. So I'll be R plus 1, and then we're going to reset columns to 0. So we've got a recursive call here. Else, we can probably print it. And so what do you think the recursive call is here? So this one says that the rows are okay, right? It says rows is less than the max amount of rows. And in this case, it says C is less than the max amount of columns. In this case, at least, right? So we know that R is less than rows. And we know that C is less than columns. And so what does that mean? Well, we're probably just somewhere in here, right? We're here, we're maybe here, we're maybe here. So what's that recursive call look like? What do you guys think? Yeah, CBay nails it, right? We're just going to increment C by 1. So all we're going to call is recursive print to again. And we're going to pass it the same out. And I do mean to say out, not C out. Always making the mistakes, right? Always making the mistakes. You're probably watching me at home. You're like, this guy, I can't believe he makes his mistakes, right? This is going to be out. 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 And we will pass R. R will be the exact same. And then C will be plus 1, right? And so I think that that's probably good. And maybe we should check to see how that works. Notice that we kind of broke it out into kind of smaller problems, right? In which we're checking for some cases here. And where ultimately, if we go past the number of rows, we're done. If we go past the number of columns, it doesn't necessarily mean we're done. But it does mean we need to increment R. So this could be considered a reduction operation. And this could also be considered a reduction operation. So let's give it a shot. I hope that it works. Because I think we did a great job. What do you know? We did it. Well done, everybody. So hopefully that's making some sense. And maybe you can even kind of use this to do this one. So now we're going to take the time to quickly do a substring. I might just kind of wave my hands here because I just want to introduce the assignment before we go. And then next week we'll kind of start on linked lists, but we're not going to be done with recursion. Because in fact, when we get to linked lists, I would much rather do things recursively than with loops. And that's just my personal opinion. I think you'll agree, but we'll kind of get a healthy mix of both anyway. And so I'm going to write a substring function. And just so I show you kind of what that's going to look like, Let's say I've got a string hello world. And if this string were to be an array, right, we'd have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, those are all the indexes. These are the indexes. This is our string. And so if I were to say substring, and the substring will look like this. It will take a string, it will take the starting location, and it will take the length of starting location. And then it will take the length of whatever string I want. So if I took substring, say string C, if I took the substring of C, and I started at index 5, and I went for the length of 2, this would be equal to, well, let's go take a look. We're going to start at index 5, so W, and I want the string to be length 2. So we should get, whoa. Let's do another one. So if I did the substring of C, and I started at, say, 2 or 3, and I went for, I don't know, maybe 1, 2, 3, 4, 5, 6. So if I did 6, then I should get low whirl, I think, right? Because there's 6 characters in that string. And then I'll show you that there will be some additional functionality for this. If, say, we did C starting at index 8, and then we wanted the string to be length 1,000, instead of making an error, let's just make it return however much that it possibly can. So in this case, we'll start at the L, and then the D, and then empty string. All right, so are you guys okay with this? If you're not, please let me know. And we're going to implement this real quick. So string will return a string. Substring will return a string. And as I said, it will be taking a string, maybe S. It will be taking an int start, and it will be taking an int length. So the base case in this sense is going to be a little hard. I'm going to ask maybe for some help if we've got the time. But I can give you the recursive call, which will just to be return the string located at the start plus the substring of S. And then we've probably got some reduction operators here. Or reduction operation. And so this one's maybe a little harder to think about. This is a string concatenation, by the way, that we're doing. And so just looking at this to start, if I called it with 5, we're going to take this W. This will be W plus the recursive call. So this recursive call needs to generate, what did we do? It needs to just generate the W. And if we were to go a little bit further, then maybe so. It would have to generate the world part of it, right? And so I said, like, we are running a little bit out of time here, so I will just kind of wave my hands. And the best way that we can do this is, at least in my opinion, and I'm sure that there's other ways that this can be done, I would like to take the start plus 1, because that will give me the next index, right? That'll give me the next character in the string. But then I actually want to take the length minus 1. So with this hint, actually, do you think that you can develop the base case for this one? I just want to know what you guys think. Because I'm doing two reduction operations here, in which I'm going to increment the starting, and since I kind of pulled out a character here, I am going to subtract one from the length. So when will this function stop calling itself? And so let me maybe come down here and we'll do these. Oh, geez. So, yeah. Yeah, no, that's exactly right. Yeah, you nailed it. But there's one thing I'd want you to look out for, is that in this case the 1000 here. And so let's actually do it like this. Let's say if length is less than or equal to 0. Let me check my notes, actually. I think I'm a little mixed up here. No, you're right. If length is equal to 0. And there's one more thing I wanted to add here. And if start is greater than or equal to the string's length. I think Red Rose kind of said something along those lines. All right, so we'll kind of wrap it up here. Maybe should have spent a little bit more time on this, but let me just prove to you that this substring function will work. And so we're just going to make sure that if the length is 0, then we don't want to do anything else, right? We're done with the substring part of it. And if start happens to be greater than the length, then we're not going to index it. So let's go ahead and give it a shot, and then I'll just quickly introduce the assignment. And like I said earlier, the assignment is going to be pretty quick, okay? So I don't need a whole lot of time. And I added a ton of comments for you already, and we even did one function for it today as well. And it's kind of a fun program. And there you have it. So we got a substring function now. And if you're ever writing some English. If you're ever writing some programs that you need to use substring for, now you've got a function for that. So let's go ahead and just take a quick look at our assignment. Are there any questions as to what we did today? Please let me know. I'm just going to pull up assignment 8 real quick. So, roughly what we're doing is, I probably can't say this right. This is an archipelago, maybe? I'm sure some of you know what that is, and maybe we can just Google it. But we're basically representing islands in code. So if you kind of look here, I wish I could get a better, this is like a really good kind of look-you-see at it. I know my face is kind of probably in the way here, but you see that there's a bunch of islands here. And they're all kind of separated. Here's a good example. I would say maybe Hawaii counts as that as well. Though there may be some more experts here. And so we're representing this by a 2 or a matrix. So if the R happens to be the color, then this is the island here. So the R, I wonder if I can do a control highlight. I can't do a control highlight. So the R's here are the island. and the X's are the water. So in this archipelago, there's only one island. In this archipelago, there's two islands. There's two green islands, separated by some water. In this archipelago, there is no islands. And in this archipelago, there's actually two islands. We do not consider a diagonal archipelago, maybe. That sounds better. Like I said, I'm a computer scientist. But it would be good if I knew what that word, or how that word was pronounced. But in this case, we've got two islands, two blue islands. The diagonal does not count as one island here. And so we're going to do some recursive functions to work with these things. So here's the class. And so we've got islands, which is the matrix. It's the 2x2 matrix. We've got rows and columns. We've got what color the islands are in that archipelago. And then we've got these two arrays, nav_r and nav_c. Notice that he's telling you here how they're initialized. And they're just to help you with the recursive functions. So if you take the row plus the column, or row plus nav_r0 and column plus nav_c0, you will be at the exact same position. If you take row plus nav_r1 and column plus nav_c1, you will go to the right by one column. So if you did that here, if you were looking at this X, then you would be here. Okay? And so if you just kind of read these, you'll see it with the nav_r2, you'll go left by one column. With the nav_r and nav_c3, you will go down by one row. And with the nav_r and nav_c4, you will go up by one row. So this is going to help you with the functions. Red Rose says you could modify this to be a battleship game. That's totally 100% right. And so there's a few things you'll have to do, so I'll just kind of pull open the code real quick since we're running out of time. I do not think that these functions are super descriptive, but I did give you some comments. There's also a video you can watch where the creator of this assignment talks about it, so you can go look at that there. But let me just show you the skeleton code real quick. So main is already done for you. Okay, and so you'll notice here that we do a red island, a blue island, looks like a white island, and a yellow island. And so here's the class. And so what do you have to do? Well, here's the constructor. So I tell you what you need to do. You just need to allocate that array and initialize some stuff. This part here might be a little confusing, but I kind of tell you exactly how that works. So just read that part. And I even kind of give you the code there. Here you have a destructor. You got to deallocate that 2x2 matrix. You've got show islands. What is this? This is recursive print, okay? I will go over this in class. I went over this in class just a few minutes ago, right? So here you go. And look, int R and C. Okay, so you can do it that way. He kind of already did these ones for you. But now you've got navigate and you've got change color. So in navigate, you're going to go through the archipelago and you're just going to change everything to an X. We are out of time at this point. I do recognize that, so just give me a few seconds. But if you're going to navigate an island, you'll kind of go through these one by one, and when you find a piece of the island, you'll mark it as an X, and then you'll recursively call, and then you'll find another part of the island, and you'll mark it as an X, and then you'll recursively call. You'll find another part of the island, you'll mark it as an X, and then you're done. Here, there's no more islands to go to, and so that's what the navigate function does. So the navigate will go through R, 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 R. And I gave you some very detailed comments here, including the nav_r, nav_c. So go ahead and take a think about it. Definitely think about this function. It needs to be recursive. And then change color is going to be done the exact same way as the navigate function, except in this case, you're going to change the colors. So instead of marking them as X's, you're going to maybe make it a yellow, 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 yellow. And that's it. Okay, so you've got 1, 2, 3, 4, 5 things to implement in this file. Just 5. The constructor, the destructor, and the show island should all be pretty straightforward. And then this will be a little bit of a puzzle, okay? I did try to give you some details, but just see if you can figure it out. Give it a shot. You've got quite a few days. It's due on Monday. Okay, so you've got almost a week. You've got maybe 5 to 6 days to work on this. So just take a think about it and let me know if you want to talk about it and need some help. And it's on Web Campus. You guys can get started at any time. So that's all I got for you today. Thanks for hanging out with me for the extra 3 minutes. Office hours are in about 12 minutes. And that's all I got for you. So I'll catch you guys next week. I hope you guys have a great weekend. Thanks for coming to the stream today. And have a great rest of your day, everybody. Thank you.